So the electrical activity of the heart is captured, recorded, collected, visualized in the ECG. And, of course, we can spell it EKG, whatever. EKG, ECG, both of them are acceptable. And I'm going to show you, if we're measuring electrical activity, you tell me what is going to be the units on, this is a graph where I'm going to draw an EKG wave for you. And you're going to tell me, what do you think the x-axis units are? Well, this is actually easy. It's time. And if you think about the amount of time for one heartbeat, like a second for a heartbeat, so you can imagine, like, go ahead and fill in, like, we're probably going to put this in milliseconds just to correlate other electrical activities. What do you think, if we're collecting information about electrical activity, what do you think are the units on my y-axis? I'm just going to scoop myself over just a tad so I have room to write. It's electricity, doggies, right? And so do you agree that it's going to be millivolts? That totally makes sense. And this middle line right here is going to be my 0 millivolts place. Now, am I drawing action potentials? Is an EKG just a picture of a bunch of action potentials? Well, sort of, but take a deep breath and write this down. The EKG is the sum of all action potentials in the heart. And if you hold really still and you don't get any other crazy, like that, input into the reading, you're going to get just the electrical activity in the heart that's being recorded in an EKG. So what do you think what's my range? How high are we going to go? How high in the positive millivolt arena are we going to go, and how low in the negative millivolt arena are we going to go? Ready? I'm going to blow your mind. That is not a typo, because I'm not typing. But it's not a typo. Oops, that was a typo. That was a typo, but now it is not a typo anymore. This is, we're talking the sum of all action potentials in your heart add up to positive 1. That's as high as we're going to go. We're not going to go higher than that. And negative 1, that's as low as we're going to go. We're not going to go lower than that. Now, why does that make you go, wait a minute, that's really weird? Because if we're adding up all the action potentials, what are the actual action potentials doing? Do they go up to positive 1 and negative 1 millivolts? Heck no. They're going down to like negative 90, and they're going up to like positive 30. So we definitely have a much bigger, like a single action potential has a much bigger range in voltage than this sum of all action potentials. So take a deep breath. You are more than welcome to go explore this further. Or you can accept that when we add up all the action potentials, there's stuff, to add them up, we're going to put electrodes on the right side, that's my left side, on the left side, on the right side, and down like on your foot or on your belly. So you're going to end up with this triangle, and within that triangle, the EKG measures all the electrical activity that is moving toward each of those electrodes, and the electrodes pick up that activity. If the electrical activity is moving this direction, it's going to subtract from the electrical activity that's moving this direction. Do you think there's any electrical activity moving this direction in your heart? Dude, think about how electricity moves in your heart. Let's throw in, you can all use your yellow pens, because I know you're all out there buying yellow pens to make this happen. Yeah, we're going to have our SA node, our AV node, which I'm going to put, I want to put it, it's going to be back here, like buried back there. right behind that vessel. And we've got all our internodal pathways heading in. We've got our bundle branch. We've got all our Purkinjes. We've got crazy branching happening on here. Yeah, look at all that action. Sometimes if we have an electrode over here and down here, and we're picking up the total electricity that's happening, then you're going to add, like, action potentials that happen in that direction are going to sort of cancel out the action potentials that happen in this direction. But the weird thing is that when you add them up so that you get the activity in one heartbeat, this is what it looks like. And how crazy is this, that this is actually true? You get a little wave that looks like this. You get a little wave that looks like this. And then you get another little wave that looks like this. And that right there is one heartbeat. So look at that. That's not even 1 millivolt. So the sum of it is really quite small, but that's all the action potentials that we added up together. The first wave is the P wave. The second, we've got a Q, R, S complex, and then we have the T wave. Nice, it's in alphabetical order. So let me tell you the things that are happening during each of these waves. The P wave. Really, we start with the P wave. So what electrical activity would you expect to be taking place during that first little bump? The atria, the cells in the atria, the autorhythmic cells, followed by the contractile cells, are all depolarizing. Depolarization. Do you agree with that? Does that make sense? How did it start? Our friend the SA node generated autorhythmic cell with that leaky pacemaker potential generates an action potential. That action potential passes through the gap junctions in the intercalated discs between all the cardiac muscle cells that are linked to it here in the atria. Internodal fibers pass between the SA node and the AV node. And while all of those are netting through the atria, the message, that action potential is passing all the way around. And all of those cells are depolarizing in whatever flavor that happens. When you add up all that atrial depolarization, that's what it looks like. Put it all together and you get this little tiny little bump. The funny thing is that it always looks like that. Whenever your atria depolarize, you get this little bump, unless you got problems going on, in which case we're going to use our EKGs to diagnose problems. Thank you. That will be super handy. It takes a little while for the atria to depolarize, and all we're thinking about are the electrical events. We're not thinking about what that causes. You can assume, what's that going to cause? If the atria all depolarize, what's going to happen next? Well, all those cells depolarized, which is going to lead to contraction, right? It's going to lead to all that calcium rushing in. We're going to let the calcium out of the sarcoplasmic reticulum. We're going to let all that calcium hook up with the sarcomeres. We're going to end up with contractile cells contracting, which we'll look at the consequences of that in the next section. When the atria depolarize, this is an electrical bump that we see. Atria depolarizing, ultimately the message gets to the AV node. Do you agree with that? The message gets to the AV node. Remember how it kind of slows down right there? There's this little bit of a pause in the AV node because we have one route through. From the atria to the ventricles, there's one way through, and the only way through is that AV bundle. Once we let the information through, once we let that electricity through, the action potential passes down your bundle branches, through your Purkinje fibers, and what's going to happen next? Who's going to depolarize next? Your ventricles. That makes sense, right? Look at the size of the QRS complex as in relation to the P wave? It's much bigger. Does it make sense to you that there's going to be more electrical activity with the ventricles than with the atria? Yeah, of course, because the ventricles are so much bigger. There's more tissue. There's more contractile tissue there to depolarize, which means there's going to be more electrical activity that's recorded. Interestingly, while the ventricles are depolarizing, what do you think is happening to the atria? The atria are actually repolarizing. Is that an electrical event? Totally. That's totally an electrical thing as well. It gets lost. The ventricle depolarization, the ventricles are so big that the atrial repolarization is somewhere in there. It doesn't get to hold its own lump because the depolarization is so big. But then after, what's the last electrical activity you're going to expect to see? And guess where it happens? Yeah, we got to repolarize our ventricles. So the T wave represents ventricles repolarize. Now, what did we just do? All we did was we mapped out and recorded the electrical activity that's going to coordinate our heartbeat. Now we know, okay, we're going to get a P wave. The atria are going to depolarize. Now we start thinking through, what's that going to cause the contractile tissue of the heart to do? At what point are we going to have atrial contraction? At what point are we going to have ventricular contraction? And really, that is going to lead us into thinking about pressure changes in our chambers and volume changes in our chambers. So let's talk about those mechanical changes next.